Okay, so we're now moving on to section 11.4. And we're going to talk about ellipses. And so ellipses are oval shapes. And these are the next of our conic sections. Let me show you how we slice a conic to get these to begin with. So now we're going to take our conic, we're going to slice it at a bit of an angle with the plane, but we're going to come in from the side a little bit more. But we're not going to be perpendicular to the vertical axis. We're going to slice it at a bit of an angle so we don't get a circle, and what we get is an oval shape. Now this is kind of a thick oval just from the way I had to construct the models, the 3D models in Lightwave to actually create this, but you can see that we definitely get an oval shape when we do this. So that's where that's where an ellipse comes from when we slice a conic. The definition of an ellipse is the locus, which again means collection, of points in the plane, or in a plane, such that the sum of the distances, sorry, my tablet's fallen asleep on me here, sum of the distances from two fixed points to any point on the locus, we'll just say on the ellipse, is a constant. So we have 2 points. And I'll call this F1 and F2. Those 2 fixed points are our foci. The plural of focus is foci. So whereas on parabolas we had 1 focus, on ellipses we have 2 foci. All right. And imagine I take a piece of string and I loosely connect it to those 2 foci. Now imagine, if you will, that I take my pencil and I hook it under the string and I stretch it up here, so that what I have is I have something that looks basically like this. Okay, so the string is now taut. And now what I'm going to do is I'm going to move my pencil everywhere I can, keeping it hooked under the string, and making sure that I keep the string taut. And when I sketch out the shape that the string allows me to sketch out, I'm going to end up with my oval shape, my ellipse. Okay, and this is the shape that essentially the planets travel around the sun in our solar system following. This is the path of the planets. So the Earth actually travels around an elliptical orbit with the sun at 1 focus. That's the idea. So if this would be the Earth, this would be the sun. And we trace out a path that looks something like this. I'll construct a nice one for you, one that looks a little less like a baked potato, in just a moment. Now, what the constant part is talking about is, I'll call this distance 1 and I'll call this distance 2. Depending on where I put my pencil, distance 1 and distance 2 are going to change. But the nice thing is that distance 1 plus distance 2 is always going to be a constant. And why is it always going to be a constant? It's always going to be the length of the string. The string does not change its length, therefore d1 plus d2 doesn't change. d1 and d2 change their sizes relative to one another, but their sum remains the same. So let me show you what happens when we go to construct one of these. Here I have focus 1, here I have focus 2, here I have a point. This is my distance 1, which is listed down here. I'm measuring the length of it. Here's my distance 2. I'm measuring the length of it. I control where this point is by sliding this control point around. Okay? And so notice that as I slide this around, d1 Distance 1 and distance 2 are changing values, but look at what happens to the sum. It's always remaining the same. And so by dragging this everywhere, it's not going to completely close just because of kind of the glitchiness of the program on this, of the construction, but we get our ellipse shape. Now, there are a couple of different ways that we can change the shape of the ellipse. One of them is to change the position of the foci relative to one another. So if I make them a little farther apart, sorry for the announcement in the background. Now we get a more elongated ellipse. So that's one way to do it. If I want an ellipse that's stretched up and down, what I can do is I can actually take this and move it up here. And now I get an ellipse that goes this way. Okay? The other thing that we can do, is we can also change the length of the string. And so if I make the string shorter, that's going to drag everything in. And now, again, I get a more elongated ellipse. So there are a couple different ways that we can change the shape of our ellipse. All right, so what's really happening here, just to give you an idea, in case you're interested. If not, you can fast forward a little bit. But what's happening is that I've created some circles, and as I change the location of this point, distance 1 and distance 2 are reallocating how the string is divided up. The circles have radii distance 1 and distance 2. And so as long as I'm moving in here, the circles are changing sizes, but the sum of those two radii is staying the same. Okay? Now when I get out here, I can't go any further because now the distances, this one's going to get bigger and bigger and bigger. This one won't catch up. They won't intersect each other any longer. And that'll be a little bit clearer. You'll see that kind of thing when we do the hyperbolas. But you can see where these points above and below are being created by the intersection of the two circles. Kind of cool. All right. Let's talk about some of the vocabulary. So when we have an ellipse, let me just kind of draw an ellipse like this. You have a point where the vertical and horizontal axes are going to come together. This is going to be your center. And the center is going to have coordinates h and k, just like our vertex did when we did parabolas, just like our center had when we did circles. Same idea. The 2 points on the ends of the long direction, notice there's a short direction and a long direction. An ellipse is essentially a circle that's being stretched more one direction than the other. In the long direction, we have what are called the vertices. So this is actually a vertex. This is actually another vertex. Together they make the vertices. The ones in the short direction are actually called co-vertices, although our book doesn't really use that terminology, but you used it in the Algebra 2 book. So you've seen co-vertices before. The long axis is called the major axis. And that's the distance from this vertex to that vertex. The short axis is called the minor axis. And that's the one from this co-vertex to that co-vertex. Now you can also have ellipses that are stretched this way. If it's being stretched up and down, then these are your vertices, and these would be your co-vertices. This would be your major axis. This would be your minor axis. And we could find the length of those. We could also talk about what's called the semi-major axis. From here to here would be the semi-major axis. It's half of the major axis because semi means half, just like semicircle. Okay. It turns out that the distance from the center to a vertex we're going to excuse me, I had to sneeze there. We're going to label A. The distance from the center to a co-vertex, we're going to label B. So on this one, this would be B, this would be A. Now, we also have those foci. And it turns out that the foci are always, no exceptions, are always located on the major axes, or the major axis, excuse me. And so somewhere in here, I have focus number 1, and somewhere in here, I have focus number 2. So I'll call this F1 and F2. Likewise, on this one, we have a focus here somewhere, and we have a focus here somewhere. The distance from the center at h comma k, let me just get rid of the label though, to the focus, we're going to call C. And it turns out that there's a relationship between A, B, and C. And that relationship is that C squared is equal to A squared minus B squared. Notice it looks just like the Pythagorean theorem, except with a minus sign instead of a plus. Instead of A squared plus B squared, it's A squared minus B squared. And it is important that A squared goes first so that this ends up being positive, because A is a bigger number than B, because it's the one that tells us which way to go in the, or how far to go in the long direction. All right, so let's move on and let's talk about ellipse equations. So our center is at h comma k. We have ellipses that go this way. We have ellipses that go this way. So notice that we have ellipses that are stretched more in the x direction, and we have ellipses that are stretched more in the y direction. These stretched in the x direction, the horizontally stretched ellipses, are going to be x minus h squared over a squared plus y minus k squared over b squared equals 1. The ones that are, so notice that A, our bigger number, is under x. So we're being stretched more in the x direction. If we're being stretched more in the y direction, then we're going to have x minus h squared over b squared plus y minus k squared over a squared equals 1. Notice since A is the bigger number, because A is always larger than B for ellipses. Now that will not be the case when we get to hyperbolas. There are some major differences between the two. We'll talk more about that when we do hyperbolas in the next section. So A is always bigger than B, because A tells us how far to go in the long direction, B is how far to go in the short direction. So long, short, larger, smaller. So now we have the a squared, the larger number, underneath y, which means we're being stretched more in the y direction. With the smaller number under x, we're being stretched less in the x direction. That's the idea. So for example, you might have something that looks like x minus 2 squared over 9 plus y plus 1 squared over 4 equals 1. So our center, and notice I'm not labeling it C because C represents something different with ellipses. Our center is going to be h comma k. Again, h and k are the opposite of what they appear to be because of the negatives built into the equation in front of them. So it's 2, negative 1, not negative 2, positive 1. Now what I'm going to do is I'm going to draw a sketch of this thing as we build it, and we'll start to fill in all of our pertinent information that they might ask you in addition to drawing the graph. So let me get a graph grid here real quick. Bear with me just a moment. Okay. So we have our center. The first thing you want to do is you want to immediately put your center on there. So my center is at 2, negative 1. I like to put a little x there because it's not an actual point on the graph. It's just the point that everything originates from. So 2, negative 1 is our center. Now, our a squared is the larger of the two bottom numbers. So a squared is equal to 9, which makes a equal to 3. Yes, algebraically it would be plus or minus 3, but technically a is a positive number because remember, a is the distance between the center and a vertex. So it's a going this way and it's a going that way. But if you want to think of it as plus and minus 3 because we have to go both directions, then that's okay. But technically a is positive. That only really makes a difference in one place. You'll see where in just a minute. So a is equal to 3. Notice that our 9, which is a squared, was under x. So this is going to be in the x direction. So we're going to go to the right, 1, 2, 3 in the x direction, and to the left, 1, 2, 3 in the x direction. Those are our vertices. So our vertices then are at 5, -1, and at -1, -1. We can just read those right off the graph. Our b squared, our smaller number, is 4. That makes b equal to 2. That's going to be in the y direction because 4 is underneath y. So we're going to go 2 in the positive y direction, 2 in the negative y direction. And now we can actually draw our ellipse in. Now make sure you make an attempt to make your ellipse as smooth as possible. Do not make it straight anywhere. Sometimes it'll come out looking more like a cigar or a little more like a baked potato or something. That's okay. Just make it as round as possible or as smooth as possible. No straight lines. There's our ellipse. So we have already found our center. We have found our vertices. The length of the major axis, since we went 3 each direction, the major axis is 6 units long. Since we went 2 each direction in the y direction or the smaller direction, our minor axis on this one is 4 units long. Now, they're going to ask you to find the foci. And the way I want you to do the foci is the following. I always want you to start by filling in the coordinates of your center, because everything originates from the center, not from 0, 0, unless 0, 0 happens to be your center. Our center was 2, -1, so I'm going to fill in a 2, and I'm going to fill in a -1. Notice I left some space after the 2. I left some space after the -1. We're now going to find our c. So let me erase this. Move this out of the way. We know that our equation is c squared equals a squared minus b squared. Now what I want you to pay attention to is the fact that this is a minus. But if you go back to the ellipse equation, remember that the ellipse equation has a plus in the middle. Notice those are opposites of each other. That's important because when we get to hyperbolas, this will be a minus and this will be a plus. They're always opposites of each other. So we know that c squared is equal to a squared 9 minus b squared 4. Notice a has to be the bigger number, otherwise c squared would be negative and it would give us an imaginary answer for c. So this is 5, therefore c is equal to the square root of 5. Again, c technically is positive because it's a distance. Remember that c is the distance from the center to a focus. So technically it's positive, but what we're going to do is, since the foci have to be in the long direction, so we have a focus there somewhere and a focus there. I'm not saying that's exactly where they go, I'm just putting them in there so we can see them. The distance from the center to a focus is going to be either the center plus c or the center minus c. The question is, which coordinate is changing? So as I go from the center to a focus, since I am moving in the x direction, then I have to take c and I have to add it to the x coordinate. And then to get the other one, I'm subtracting it from the x coordinate. So we do 2 plus or minus rad 5 comma -1. Now obviously if that was a 5 and not a rad 5, you would have to do 2 plus 5, which is 7, and 2 minus 5, which is -3, both with a comma -1 after them. But because we can't combine those like terms, you just leave it like this. Now what if it was going up and down? Well, if this was being stretched up and down, then our foci would have been up and down, and we would have gone c square root of 5 units in the y direction, so we would have done plus or minus square root of 5 after the -1 instead of after the 2. But always start with your center. Okay? Don't start by finding c and trying to figure out where those things go, because what people tend to do is they tend to treat it as if the center was at 0, 0. And that's not where our center is necessarily. Okay, so there's our center, our vertices, our foci. We talked about major and minor axes. The last thing we need to talk about is something that's called eccentricity. Eccentricity is a measure of how far a conic section has been deformed from a circle. A circle has an eccentricity of 0. It is still a true circle. as we start to smush the circle together and make it kind of bulge out on opposite sides and make it into an ellipse, the eccentricity increases from 0 to 0.1, 0.2, 0.3, etc. It can be anything in between. It doesn't have to go by 0.1s. Okay? So maybe this particular one has an eccentricity of something like 0.7, okay, or 0.81 or something along those lines. So for ellipses, the eccentricity is going to be between 0 and 1. This is only for ellipses. Once you get above 1, then you end up with hyperbolas. Okay? So the eccentricity is going to be a number between 0 and 1 when we deal with ellipses. And the way you find eccentricity is very simple. Eccentricity is equal to c divided by a. Since c and a are technically positive, eccentricity is always positive. So this is going to be our c, which is the square root of 5, divided by our a, which came out to be 3. So there's our eccentricity. Center, vertex, foci, eccentricity, graph. Okay, so I'll try and wrap this up as quickly as I can. I have two more examples to show you. One is what we saw with parabolas, and that is what happens if they don't give it to us in standard conic form. And again, you did these in Algebra 2, so I'm going to go through this kind of quickly. You can rewind it if you need to. But I want to try and keep the video short. I know it's too late for that, but we'll do the best we can. This is an ellipse because notice x and y are both being squared. It can't be a parabola if they're both being squared. Parabolas only have one variable being squared. They're also being added together. And notice the coefficients are different. If the coefficients are different, these are both squared and they're being added, then it's an ellipse. If the coefficients were the same, both being squared and being added, that would be a circle. That would mean it's being stretched the same amount in the x direction and the y direction. These being different indicates that it's being stretched a different amount in both directions. What we do now is we're going to group our x's together. I'm going to leave some space, and then I'm going to group my y's together. Notice I'm keeping all the pluses and minuses in the same place. And now this guy I'm going to move over to the other side by subtracting it. In this case, subtracting. On another equation, maybe I would have had to add it to move it over. So what I did was I broke these apart because we now need to complete the square, just like we did with parabolas. The only difference is now we have to complete the square not once but twice. Once on the x's, once on the y's. So here, to complete the square, remember it has to be 1x squared. But I don't want to divide everything through by 4, because if I divide everything through by 4, that's going to completely mess up the y's. So what I'm going to do instead is I'm going to factor the 4 out of just the x's, which leaves me x squared minus 2x. Likewise, over here, I'm going to factor a 9 out of just the y's. So when I take that out, it's y squared minus 6y. Notice that the stuff in the parentheses I can now complete the square on because it's 1x squared and 1y squared. But leave those factors out in front. They don't disappear, not at this point in time. Half of negative 2 is negative 1. Square it is 1, so I'm going to add 1 here. And that means I have to add 1 here. The only problem is when you do that, you lose your equal sign. Why do we lose the equal sign? We lose the equal sign because by putting a plus 1 here, we did not make the left side bigger by 1. We made the left side bigger by 4 because that plus 1 is inside a parentheses with a 4 attached to the outside. When we distribute that 4, we really make the left side bigger by 4. Even if we don't distribute it, we still made the left side bigger by 4. So what I have to do is I have to add 4 to this side because that's really what I added to the left side. Once I do that, my equal sign comes back. So you've got to be very, very careful with that. Now we're going to complete the square on the y's. Half of negative 6 is negative 3. Square it is 9. But I can't add 9 to this side because I really added a total of 81 to this side. If I make the left bigger by 81, I have to make the right bigger by 81. So there's my completing the square. Now I have to factor the parentheses. This becomes x minus 1 squared plus 9 times y minus 3 squared equals, and we have 85 minus 49 is going to give us 36. So we're almost done with our equation, but remember that on ellipses we have to have an equals 1. And the way we get it to be equal to 1 is we divide both sides by whatever number is currently over here. And what will typically happen, not always, but typically, that'll give you your 1, these will typically reduce. And 4 and 36 cancel and give you a 9. So that's x minus 1 squared over 9. And these will cancel and give you a 4 plus y minus 3 squared over 4 is equal to 1. Here's our equation, and now you can graph it and do everything else with it just like we did the last example. Now it's in standard form. So follow the stuff we talked about in example number 1. Okay, the last example I want to talk to you about is the reverse engineering problems. And the way that works is maybe they'll give you something like an ellipse, and they'll tell you that the foci are at plus or minus 3, 0. And the vertices are at plus or minus 5, 0. Again, I apologize for the announcement in the background. So the key to doing these, just like with parabolas and just like we're going to see with hyperbolas, is you need to sketch the graph to see what's going on. So let me pull a graph grid up here. And so at plus or minus 3, 0, we have our foci. I'm going to put little f's above them. At plus or minus 5, 0, I have my vertices. I'll put little v's above them. Notice this clearly shows us, because of vertices and because of foci, that this is being stretched in the x direction again. What we don't know here is how far up and down this is going to go. All we know is this thing is looking something like this. Sketch it in. It's not meant to be a perfect graph. It's just meant to organize our information. So because this is being stretched more in the x direction, that means that x minus h squared is going to go over a squared again. And our y minus k squared has to go over our b squared. Again, if the vertices and or foci were going up and down, then the a squared would be with the y instead of with the x. Then we have our equals 1. Our job, fill in h, k, a, and b. Now clearly we can see from this, because of the symmetry, that our center is right here at 0, 0. So that means since our center is 0, 0, our h and our k are 0, so that just leaves us x squared over a squared plus y squared over b squared equals 1. So anytime you don't see an h and or a k, that means that those coordinates were 0. Now we have to find a squared and b squared. Remember that a is the distance from the center to a vertex. 0 to 5 is 5 units, so a equals 5. So we know that this is really x squared over 5 squared plus y squared over b squared equals 1. Now, we don't know what b is, though, but we do know what c is, because c is the distance from the center to a focus. And so c is equal to 3. And we know that c squared equals a squared minus b squared. 3 squared is 9. 5 squared is 25 minus b squared. So negative 16 equals negative b squared when we solve for b. B squared equals 16. Now, I don't need to go any farther. I don't need to solve for b, because I'm trying to find b squared, which I now know is 16. There's our equation. So I apologize, the video ran a little bit long, but I warned you guys that was going to happen to get all the information in. So go ahead and rewind it as necessary to look at the parts you have trouble with, and we'll take a look at this in class tomorrow.